Hello everyone, and welcome to our video presentation on experiment number 4, implementation of hidden Markov model. In this session, we will dive into the objectives of the experiment, the implementation of the program, and the execution, result, and various application. The main goal here is to implement hidden Markov model and understand its functioning in the context of sequence prediction. Basically, HMMs or powerful statistical models used in various fields, including speech recognition, bioinformatics, and natural language processing. Uh, then we'll see it with program. Uh, this code utilizes the forward algorithm to calculate probability of observing given sequence of symbol with HMM models. At the outset of the code, we imported the NumPy, a powerful library in Python for numerical computing, which facilitates efficient handling of arrays and matrix. Then we have initialized the t underscore m and filled it with a array. Basically, it's a transition matrix. It will be further discussed. Then under that t underscore m, we have declared e underscore m. It's an emission matrix. It will also be discussed later. Under that, we have initialized the initial probability and the observed sequence. These matrices are at the heart of hidden Markov model. The transition matrix defines the probability of the transitioning between hidden states, while the emission matrix represents the probability of emitting observable symbols for each state. For instance, let us take an example in weather forecasting scenario. The transition matrix might be denoted the likelihood of transitioning from sunny day to rainy day, while the emission matrix could represent the chance of observing certain weather conditions like cloudy or clear sky. Okay. Uh, Moving forward, we define the initial probability for the starting in each hidden state. This probability indicates likelihood of beginning uh, in a particular state. For example, in our weather example, the initial probability might represent the chance of starting the forecast on a sunny or a rainy day. Historically, sunny days may have been more common. We would assign a higher probability to starting in sunny state. Okay. Under that, we have declared a O underscore S. It's observed sequence. These are symbols we observe over time, represented here as a sequence of binary ones and zeros. For example, continuing with our weather analogy, the observed sequence could be represent daily weather observations, where one might denote as sunny and zero will be denoted as rainy day. Here comes the core of the program, the forward algorithm, uh, which dynamically approaches iteratively compute forward probabilities for each time steps. Example, imagine we are forecasting the weather for the next few days at each day. We consider the probability of observing the given weather condition based on the previous day forecast and the probability of transitioning between the weather states. These lines computes the forward probability of each hidden state at the current time step. It factors in the emission probability of observing current symbols from each state, multiplied the number of probabilities of transitioning to the state from all previous states. Finally, here we summed up the forward probabilities at the last time step to obtain the overall likelihood of observing the given sequence. This gives us the insights of how probable it for a sequence to occur according to our hidden Markov model. So that's the comprehensive breakdown of the code implementing